Hello everyone, this is lecture 4 of the Statistical Computing and Machine Learning course. I'm Professor Zabaras, and today we'll continue some of the basic elements of probability and statistics that we're discussing over the last 3 lectures or so. And so let's see what type of topics we're going to continue covering today. So we're going to talk about the joint distribution of 2 random variables. We're going to define the probability density of 2 random variables, talk about the marginal and conditional densities, introduce things such as conditional expectation, and extend all of these ideas to multivariate random variables. So with that done, we will discuss a little bit about covariance and correlation versus independence that we have seen in the last lecture. We're going to talk about the covariance matrix for multivariate random variables. We're going to talk about the correlation matrix and correlation coefficient. A little bit of relation of how correlation relates with the degree of linearity in the data, and also how correlation is useful or not when we have noisy or nonlinear relations between our data. So at the end of the day, we're going to finish discussing a little bit about, since we have seen lots of different type of distributions, we would like to know if we change variables, if we transform variables, how do the different densities are transforming. So if y is a function of x, what's the relation of the density of y with the density of x? So we will see how random variables transform, and we will conclude actually that what we know about the transformation of functions is not quite the same as transforming PDFs when we change variables. Okay, so the goals for today's lecture is to understand the difference between independent and uncorrelated random variables, to learn about marginal conditional densities, and also how Bayes' rule looks in the form of densities, and also learn how to compute densities when we change variables, when we have transformation of variables. So the references remain the same as in the first 3 introductory lectures, so I am not going to repeat this. Okay, so let's consider that we have 2 random variables x and y from the sample space omega to the real line R. So we're going to define the joint probability density of these 2 random variables as pxy, defined through this equation that you see on the top. So on the left hand side, what I have is I have the probability of the event that x belongs to A and y belongs to B, which, if you want to see it in the context of events in the sample space omega, is basically the probability of the events that through the transformation x are mapped onto A, and similarly this y minus 1 of B is the subspace basically of omega that through the transformation y is mapped into B. So we define this probability density of x belonging to A and y belonging to B as being this joint density that you see here. All right, so now let me introduce the concept of the marginal density for these 2 variables x and y. So let's say that, for example, the variable y belongs anywhere in the real line. So basically any value of y is acceptable, is always true. All right, so basically y belonging to R is, if you like, is an event that always happens. So effectively this joint distribution in this case becomes equivalent to the probability that x belongs to A. Okay, and you remember from an earlier lecture, we wrote this in terms of the density p of x, dx integrated on the domain A of the real line. So if we use the definition of the joint probability density from the first equation for these two events here, we're going to have an integration in A for X and an integration in R for Y. And you can immediately see that P of X becomes this integral of Pxy dy over the real line. And this is what we define the marginal density of X. Okay, so what we have done up now is we define the joint density P of X and Y of two random variables X and Y, and now we can see that the marginal density P of X is basically can be derived by integrating Y out from the joint density P of X and Y. We can extend the idea of independent events that we have seen in earlier lectures to the probability densities, and we can show that two random variables are independent if P of X and Y is P of X times P of Y. So I want you, when you look at these equations, again, these are not probabilities, these are probability densities, right? But the idea of independence for events is also true for density, so we can write it like that, where P of X and P of Y are the marginal densities of the joint distribution P of X, comma Y. Okay, so we introduce P of X and Y, we introduce the marginal density of X, and similarly you can write the marginal density of Y. So someone at this point may wonder, can I actually introduce the conditional density, and can I write something that looks like Bayes' rule, but in the context of densities, not probabilities? And the answer is yes, we can do this. And the way we're going to actually derive something like that, so the equation is going to look like that. So the Bayes' rule in terms of, or the product rule at this point in terms of densities is going to look like that. So let me see how we can derive this. So what I'm going to do, I'm going to take two events, an event of X belonging in the interval A to B, and an event of Y belonging to the interval Y minus epsilon and Y plus epsilon as epsilon goes to 0. So in principle my event is that capital Y is equal to little y. So obviously this conditional probability can be written by definition, if you like, as an integral of the conditional density P of X and Y dx integrated from A to B. Don't pay attention to what this thing inside the brackets is, but I can write this left-hand side as using as a definition of the conditional density of P of X given Y. All right, I can write this as the integral from A to B of P of X given that Y takes the value Y dx, and I write here the value Y, capital Y equal little y, because I'm going to make my epsilon to go to 0. So what I also can do is, because this is the conditional probability for two events, I can write this as the joint probability that X belongs to the interval AB and Y belongs on this interval Y minus epsilon, Y plus epsilon. And I can express this with the double integration that you see here in terms of the joint density. And the denominator, I can write this in terms of this integral that involves the marginal probability density of Y integrated from Y minus epsilon to Y plus epsilon. Now these integrations in Y, because epsilon is going to go to 0, they become, so this integration here becomes P of Y times 2 epsilon, and the integration here becomes 2 epsilon times P of X comma Y, and then I have my integration in X from A to B. Okay, so if I cancel the 2 epsilons, what I get is P of X comma Y divided by P of Y. So immediately you can see that the conditional density of P of X given Y is really the joint density of X and Y divided by P of Y, And effectively this leads to our equation that is familiar from the Bayes rule for events, but now it is written completely in terms of the densities. So effectively what we have learned in terms of events also transforms to the same sort of equations in terms of probability densities, and that's the equation that you see in the bottom of this slide. Okay, so let me say a few words about the conditional expectation. So let's take two random variables again, mapping events from the sample space to the real line. I am going to define the conditional expectations I have done in an earlier slide of x given y this way, where the only change in my definition of expectation is I'm using the conditional density instead of the marginal density. And now what I'm going to do is I want to use this conditional expectation to define the expectation of x. So what I'm doing is I'm using my standard definition of the expectation of x that you see in the left hand side. All right, so I have x times p of x, and p of x we know is the marginal of p of x and y integrated in y, and the joint here can be written as p of x given y times p of y, right? So I can plug in all of these things and rearrange terms. And if you rearrange terms, if you pay attention to these equations, you can see immediately that you get here the conditional expectation. That's this parenthesis. And then this conditional expectation is averaged with y sample from the probability p of y. So effectively, we have this nice formula on the bottom that says that the expectation of x is this integral of the conditional expectation of x times py dy. Okay, so it's the average of this conditional expectation with respect to the distribution p of y, which in some sense is the expected answer. And I think I had already commented that this type of equation will be useful in many applications because this conditional expectation may be easier to actually evaluate than evaluating directly E of x. So if this is something very easy that we can analytically compute its expectation with respect to py, this would be a nice formula to use in our derivation. All right. So let's move from real valued random variables to vector random variables. So we have x being a vector with components x1, x2 to xn that you can think of this as a function in essence that maps the sample space to Rn. All right, so I have n components here. So here each of these components is a real valued random variable the way we have seen it up to now. So we can extend practically everything we discussed up to now to these multivariate random variables. So we can define a probability density, and in doing so we're going to start with the definition of the cumulative distribution function evaluated at little x1, x2, xn, defined as the probability of capital X1 being less than x1, capital X2 less than little x2, capital Xn less than little xn, and then we can define the density of the vector x as this nth order derivative that you see on the bottom. All right, and here of course we are going to assume that this density is normalized, so we're going to have also this constraint that you see at the end, that when we integrate for all possible values of x, this comes equal to 1. All right, so nothing different here. Once we have the cumulative distribution function, we can introduce the density for this multivariate random variable the way that you see on the bottom. Okay, the expectation, we can define it exactly as we have done before, but now notice that x is a vector in Rn, and our integration is going to be in Rn. We can also define the expectation of each of the components of x. So if, for example, if I want the expectation of xi, I can take xi, integrate it with p of x, all right? And the nice thing is I can actually write this as xi times p of xi dxi, where p of xi is the marginal of p of x. And what has happened to all the other components, because here I only have xi, all the other components I can actually integrate them out, and the only thing I get here is the marginal p of xi. So let's go back to two random variables x and y from the sample space to the real line. I can introduce the covariance. We already did this in the last lecture with this definition that you see here. You know, if you expand this expression, you can actually see the more familiar formula that the covariance is the expectation of the product xy minus the expectation of x times the expectation of y. And we already introduced the idea that if x and y are independent, then this expectation of x and y can be written as the product of e of x, e of y. That basically comes by only accounting for the fact that the joint density of x and y is the product of the marginals of x times the marginal of y. So independence leads to zero covariance, so independence leads to what we call uncorrelated random variables, and we already mentioned the opposite is not true. So if the covariance is zero, it does not mean that the random variables x and y are independent. Just remember that independence is a very strong relation between two random variables, because it's a relation that involves probability densities. Correlation involves expectation, so it's a weaker statement. All right, so we can also define sort of a normalized covariance between two random variables x and y, and you can see here the normalization happens by dividing by the standard deviation of x times the standard deviation of y, where I remind you the definition of the standard deviations. Sigma x is the square root of the variance of x, and sigma y is the square root of the variance of y. I should actually simply put variance there instead of covariance, so that's a typo that I will be correcting in the post-it slides with this lecture. And I believe we also introduced in the last lecture normalized random variables x and y in a way that effectively gives us mean to be equal to 0 and variances to be equal to 1. And I mentioned if you have data sets, one of the first things in practically every machine learning task would be to normalize your variables in a fashion similar to what you see in these two equations on the bottom of this slide. All right, so again, that's the definition of the variance. Nothing new, and the covariance between two random variables, all right, is given like that. And one of the things that I would try to emphasize in the lecture today, that we have not seen this before, that this measure of covariance expresses basically the extent to which the variables x and y vary linearly together. And the key buzzword here is linearly, all right? So this covariance is not going to be a good measure of how x and y relate to each other when their relation is nonlinear, okay? We already have stated that if x and y are independent, the covariance vanishes, all right? So nothing new there. Uncorrelated random variables is when the covariance is equal to 0. We mentioned that independent leads to uncorrelated random variables, and the opposite is not true, because covariance again is an expression that involves expectations, but independence involves a much stronger relation between PDFs. You may see here and there in different applications another definition that is called orthogonality between random variables, and usually orthogonality implies that the expectation of x times y is equal to 0. So in that case, you may see expressions that such as the expectation of x plus y squared is the expectation of x squared plus the expectation of y squared. All right, so that's the relation of orthogonality. And when we come back, I will remind you, so you don't really have to remember this. Is better to have a good use and connection with this definition of uncorrelated random variables, and we will wait for this when it comes to particular applications. Okay, so if I go back to these vector random variables like x that you see here, I can introduce the covariance matrix in the way that you see here, and you notice it looks similar to what I had before, but because x is now a vector, right? So here I'm going to need to use x transpose. That's the outer inner product, right? X transpose effectively will give me a matrix, average obviously by the definition, right, of the covariance with p of x, and this is what we call the covariance of the vector random variable x. That's a matrix that is n by n, assuming that my random variable is in Rn. All right, a few details about the covariance matrix. If you want to take the ij component, you're going to have to use the I component of this vector and the j component of that vector, and this is what you see here. And immediately from this equation, you can draw the conclusion that the covariance matrix is symmetric. So if you make this j, if you make this an I, the answer remains the same. And so the covariance is symmetric. This is very nice. And even more important, the covariance matrix is positive semi-definite. So I'm not going to go through the whole derivation here, but I remind you the definition of positive semi-definite is if you take any vector v that is not equal to 0, v transpose covariance of x v is greater or equal to 0. Okay, so if you follow the algebra, just one line, you will see that's the case. So the covariance matrix is both symmetric and it is positive semi-definite, and this is certainly two properties that are significant and will make a lot of simplifications in many of the algorithms where the covariance matrix is coming to play a significant role. If you take the diagonals of the covariance matrix, and this is what the equation on the bottom shows, you actually get a very familiar result that the II component of the covariance matrix of x is nothing else but the variance of xi. And the only thing that is involved is integrating basically the density p of x in all the other directions except xi. Okay, so when you do that, you actually get directly in front of you the definition of the variance of xi. So the II component of the covariance of a vector random variable is the variance of xi. So here again is this symmetric positive semi-definite covariance matrix, and the diagonals again are the variances of the different components of this random variable. And often, as I mentioned, we normalize this covariance matrix using correlation components, and here is the correlation matrix where every component has been normalized, and I give you here the definition of the correlation coefficient between two random variables x and y is basically the covariance between x and y divided by the standard deviation of x times the standard deviation of y. Now, what exactly does this correlation matrix does? Well, the nice thing is that I'm going to show you next that these coefficients, these correlation coefficients between two random variables are between -1 and 1. So in essence, this normalization makes much easier to discuss about the linear correlations between random variables than using directly their values here. I mean, you can imagine how messy it would be if one variable, let's say, take realizations that they're equal to 1, and another random variable takes realizations that they're equal to 1,000,000. It's very difficult to be able to actually see the results clearly, but this normalization brings all of these coefficients that you see in the correlation matrix between -1 and 1, and this is what I'm going to show you next. So the correlation coefficient between two random variables x and y is between -1 and 1. I am not going to do the proof of this. It's given on this slide, and the algebra is trivial. What you need to do, for example, to show that the correlation between x and y is greater than or equal to -1, start that the variance of this new random variable is greater or equal to 0. Use the definition of this random variable, expand it as you can see, and eventually, because this is always greater or equal to 0, you can show that the correlation coefficient is greater or equal to -1. And similarly, if you start with the variance of this new random variable here, being greater or equal to 0, you can see that the correlations of x between x and y is less or equal to 1. So the correlation coefficient is between -1 and 1, and that's very useful. So this is a summary of what we already have used. If we have two vector random variables, all right. So if you want the covariance is the expectation of x minus e of x times y minus e of y transpose. You can explicitly, if you expand this, write it like that, if that helps you. All right, and the covariance between the components of a vector. So if you take y to be x, and you want to find how, what's the covariance between, let's say, the component x1 and component x5, if you want to represent all of this, you can use the same expressions before for y equal to x. So it is given like this, so nothing new there. And so let's visit this idea of correlation now in more detail and try to clarify a lot of potential ambiguity that exists when you take undergraduate courses and professors introduce the concept of correlations. So let me take two variables that are related linearly. So y equal alpha x plus b, and in one case the slope here of this line is positive and another one is negative. You can show that if y and x are related by this linear relation with alpha positive, then the correlation coefficient is equal to +1. If they're related via this linear relation with alpha negative, the correlation coefficient is equal to -1. So you can immediately see what I noted before, that the correlation coefficient between x and y captures the extent of the linearity between two random variables x and y. Okay, and if the slope is positive, the correlation coefficient is +1. If it is negative, the correlation coefficient is -1. Okay. Now, so the correlation coefficient is the degree of the linearity, right, that we use here. And we already stated that if two random variables are independent, they are uncorrelated. Okay, so the correlation coefficient is 0. But the converse is not true. Uncorrelated random variables does not imply independence at all. Okay. So I'm going to show you a number of examples that actually this demonstrate that this is not the case, and also I'm going to show you an example where this concept of correlation can become murky when you try to use it between data x and y that vary non-linearly, because we will see in that case the correlation coefficient doesn't really mean very much. Okay, so before I do any of the above, let me go something that I mentioned maybe on lecture 1, on lecture 2. So I remind you that somewhere we used before that if we have the sum of independent random variables, then that sum, the variance of that sum, can be written as the sum of the variances of each random variable. So for example, if x and y are independent, the variance of x plus y is the variance of x plus the variance of y. And I'm proving this thing here by expanding the definition of the variance of x and y, simple algebra, and using the fact that two independent random variables means that they're uncorrelated. So this term drops to 0. So you can see that the variance of x and y is the variance of x plus the variance of y. So we used this before for many random variables. If they're independent, the variance of their sum is the sum of the variances of each of those random variables. And we also use a similar expression for the expectation that you see on the bottom. And I remind you, this equation for the expectation does not require any independence between the random variables x and y. The equation on the bottom is valid all the time, but the equation that you see regarding the variance requires that the covariance matrix basically is 0. All right, so let's do one example of two random variables that relate nonlinearly, and it's going to be a very simple example, and you can read the details in the slide, but I'm going to take x to be a uniform random variable between -1 and 1. I'm going to take y to be x squared, all right? And I'm not going to show to you, I'm going to just go through the algebra shown in the slide. Obviously, you can see here these variables are not independent, right? Y is equal to x squared. Strong dependence there. But I'm going to show you in this slide that the correlation coefficient between x and y is equal to 0. So if you calculate the expectation of x and the variance of x, easy to do because that's a uniform random variable. You can also calculate the expectation of y. Y is equal to x squared, right? So you can write the expectation of x squared as the variance of x that you know, and the expectation of x squared, which you know. So you can compute the expectation of y, and also the expectation of x and y. Y is x squared, so that's the expectation of x cubed. You can compute it, it comes to be equal to 0. And you can plug in everything at the correlation coefficient between x and y, and surprise, surprise, the answer comes to be equal to 0. So we have the correlation coefficient between x and y being 0. So this equation will tell you, oh, they are uncorrelated, but you can see they may be uncorrelated when we use the covariance measure for what we define uncorrelated random variables, but these two random variables, they strongly depend on each other because y is equal to x squared. Okay, so for data for variables that depend nonlinearly, you have to be very cautious, and I may say you should not use the covariance as a measure of the independence of these random variables. We will see maybe in one or two lectures that there is a measure that actually is a true measure of independence, and it goes with the name mutual information, and so I will postpone any discussion or definition of what mutual information is until we actually reach the lecture notes on information theory. So if you can wait one or two lectures, you will see that there is a better measure that actually is applicable all the times, that captures independence between random variables. Okay, so what I want to do is I want to show you with data these limitations, if you like, of the definitions of using the covariance as a measure of independence and correlation. And so what we have here is we have a bunch of data, all right? So on the top you will see all the numbers that you see listed for each data set is the correlation coefficient that we defined before. So in this case you can see we don't have noise, or the noise is infinitesimal, and we said if we have a linear relation with a slope that is positive, the correlation coefficient is 1. If the slope is negative, the correlation coefficient is -1. Now for all the other data sets, you notice the correlation coefficient is between -1 and 1, and in some extent it takes it measures not only the orientation of the data. So for example, you can see this in average looks like a linear relation with positive slope, the same here, but this data set has more noise, so has less correlation coefficient than this data set that has less noise, and than this data set that has no noise. And similarly for the negative slope cases. So in some ways we can see here the correlation coefficients that we compute, not only they account for the degree of linearity in the dependency of the data, but also the noise level, if you like, that we have in our data set. Now in the middle we don't have any noise, all right, and you can see if the slope is positive, the correlation coefficient comes to 1. If the slope is negative, the correlation is -1. That's nice. Now in the middle slide, the data are in the x-axis, so the variability in the y-axis, so the standard deviation sigma y is equal to 0. So by the definition of the correlation coefficient, you remember the correlation coefficient is the covariance divided by sigma x times sigma y. So if sigma y is equal to 0, the correlation coefficient is not defined for this case, and that's why you don't see a number. So finally, we have all this data on the bottom. Obviously, the dependencies between this data is highly nonlinear. But if you go and you actually use the definition of the correlation coefficient for all of these data sets, the correlation coefficient comes to be equal to 0. So that's interesting, isn't it? So we have data that imply that they are not correlated, but somehow the relation between these data sets, x and y, is very strong, and it's very nonlinear. Okay, so the correlation coefficient, in conclusion, it is a measure of the linear relation between the random variables, but also of the noisiness in the data, and also to some extent of the nonlinear relation between the data. Okay, so you should use always the definition of the covariance as a very cautious measure of the independence of random variables, because in many cases when you have noisy data or when you have nonlinear relations, it is not an acceptable measure of independence of those random variables. We will come back to this topic of course when we discuss information theory and we introduce this idea of mutual information. All right, so let me since I'm talking about I'm going to be talking next about transformations between random variables, so maybe the easiest thing will be to start with a linear transformation between two vector random variables x and y, and you can see this relation here, y is ax plus b. Okay, you can show by using the definition of the expectation, the covariance of vector random variables, that the expectation of y is a times the expectation of x plus b. The covariance of y is a times the covariance of x a transpose. Pay attention, a transpose, not a transpose covariance of x a, right? It's a covariance of x a transpose. And you can actually also do the most simple case when y is a scalar random variable, and it is a transpose x, where a is a column vector, plus a scalar b. So in that case, you can also write down the expectation and the variance of this scalar random variable as a transpose ex plus b, and a transpose covariance of x a respectively for the expectation of y and the variance of y. All right, so let me try to finish the lecture today with a discussion on how do densities change when we have transformation of random variables. So if somehow I give you the density of a random variable x and I take some transformation of x, f of x, how does the density of y equal f of x for a nonlinear function, let's say f of x, how will that PDF looks for y? Now, the obvious thing, somebody, if you are working with functions, right, and you have, let's say, a transformation x as g of y, and I give you the function f of x, and you want to find the function in terms of y, you will go and plug in where you have x, you will put g of y, and you say, that's my new function in terms of y. Well, yes, you can do this with functions. You cannot do this with probability densities. So probability densities do not transform as functions. You have to account for, if I can say, for conservation of probability mass. And if I can go to this equation that you see on yellow here, my second equation, this is the equation that is going to allow you to go from the density of x to the density of y when you change variables from x to y. So what it says, the probability in being in the interval delta x is the same as the probability in being in the interval delta y. And if you rewrite this for both increasing or decreasing functions g of y, the general formula, you can see from here I have dx over dy, but the general formula to compute the density of y will be to plug in the density of x, g of y. That's what you will do with functions, but then you have to multiply with the absolute value of dx over dy. So this is the absolute value of what I call the Jacobian of the transformation from between x and y, right? So dx over dy accounts for the transformation, and the Jacobian is a good measure, is a good metric that tells me how distances in x vary to distance in y for the scalar case. And so here I have an absolute value, and I notice the way that I expanded this formula. If dx over dy is the derivative g prime of y, and I put a scalar s that can be minus 1 or 1, right? So if this derivative is negative, you make s to be negative 1. If this is positive, s equal to 1. I think you will be better off if you write this as the absolute value of dx over dy, because that's the way I want you to remember. But if you need to do algebra, if you need to take, for example, another derivative, you may need to write this as plus minus 1 times the derivative of g with respect to y. So again, what do you need to remember when you transform variables and you need to find new densities? That the mass, the probability of being in the interval delta y is the same as the being in the probability in being in the interval delta x. Once you do that, you can write the density of p of y in terms of p of x and the Jacobian dx over dy. So somewhere in, I think in the previous lecture, we gave the definition of the gamma, probability density, and so this is the density for the gamma distribution given like that. And I mentioned to you that if you change variables and you define y to be 1 over x, then the probability of the density of y follows what we call an inverse gamma distribution given by this formula. And again, if you do it carefully, you're going to take the density of x, right? Instead of x, you're going to put 1 over y. You do this here in these first 3 terms, but also you have to put the absolute value of dx over dy, and dx over dy is minus 1 over y squared, so you have absolute value 1 over the y squared, and this is how the inverse gamma distribution comes. Okay, if you don't have this term and you simply plug in x to be 1 over y in the gamma distribution, you will of course get the wrong answer. Okay, so be very careful when you do transformation of variables and you go from one density to another. So the inverse gamma distribution for y in this case is given by the density is given by the formula that you see in the bottom. Now you may wonder, can you extend this calculation to vector random variables? Of course you can, right? I mean, the same way that you do integrals in one dimension and integrals in Rn, you can do change of probability densities as you move from x to y in Rn. And the only thing you will need is, you will need the absolute value of the determinant of the Jacobian, and here I have the Jacobian del x del y, which is the inverse of this del y over del x matrix that I have here. Okay, you can write directly del x over del y, but if you if you're given y as a function of x, this is the matrix that you can calculate in a straightforward manner, and then you invert this, you calculate the determinant, you take the absolute value, and this gives you the density of y, where for x you put the corresponding value of y the way you will do when you change variables. Okay, so the density of y is the density of x times the absolute value of the determinant of the inverse Jacobian, if you like. Okay, I have an example that I'm not going to go through this because it's rather simple. If somebody gives you the density in two random variables x and y that signify Cartesian coordinates, you can actually change the random variables to polar coordinates, to r and theta, and you compute the joint density of r and theta, and you will see from the equation, the first equation I have here, this determinant of this Jacobian here is going to give you a measure r, and this is what makes the difference. So you can take your standard density in x and y, plug in x equal r cosine theta, y equal r sine theta, but you have to multiply by the determinant of the Jacobian, which is equal to r, and this is the correct density in r and theta. Okay, let me finish with one comment and one schematic, and I can go directly to actually the schematic. I believe this example coming from Bishop's book. So let's say that you have a distribution p of x, looks like a nice Gaussian to me, okay? And so this is my nice Gaussian, p of x, and I do a transformation of variables. Let's say I transform x using this g-1 mapping to some variable y, and I want to calculate the distribution p of y, and in particular in this picture I'm interested to calculate the mode of the distribution p of y. So the first obvious thing that somebody may do is take the mode of p of x and map it through g-1, right, and say this is the new mode of p of y. But actually, as you can see from the histogram of the random variable p of y, this point is not the correct mode of p of y. And why is that? Because you remember, to find the mode of the distribution, right, that's where the distribution becomes maximum. So you have to take the first derivative and set it equal to 0 and compute the corresponding value of y where that derivative becomes 0. And if you use the change of variables for PDFs between the PDF for x and the PDF for y, you remember there is a g prime of y here. That's the derivative of that mapping from y to x. Okay, so here when you take derivatives of this with respect to y, you're going to get one contribution from this first term, which is given here. All right, so you're going to get the derivative of the density using the chain rule times the derivative of g. So you're going to get the derivative of g squared, plus now you're going to get this times the second derivative of g. Okay, so this second term is actually what is going to make the difference, and it will not give you that the mode of P of y is actually the mode of P of x transformed through the inverse mapping G inverse. Okay, so you have to be careful when you use these transformations and you try to make decisions as to where the mode of the new PDF lies. Now, how do we get this graph? Actually, the graph, you can get it simply by using samples. And so you can sample, let's say, your x from your distribution P of x, all right? And then for each sample x of s, you can map it through the transformation G inverse to get samples of ys. But when you put all of the samples together, the mode of py will be different from the mode of p of x because of this second term that you see in here. All right, so that's all for today. We're going to move in the next lecture in 2 days to discuss the multivariate form of some of the distributions we have seen. So we will talk a little bit about the multivariate student t distribution and of course the multivariate Gaussian distribution. So hopefully in a few lectures we will be ready to start doing some real machine learning tasks without having to bother about the algebra and the machinery that is coming from probability theory. And so until then, have a good day, and I will see you in 2 days for the next lecture. Bye.